Welcome to 4.1 Implicit Differentiation. In this section, we're going to be talking about what are called implicit functions and how we take the derivative of them. Excuse me. Up until this point, you've dealt with mainly explicit functions. Explicit functions are defined as y equals, and everything on the other side of the equal sign is an x value. Implicit functions means that we have either y's on both sides of the equal sign or x's and y's mixed in together on the same side of an equal sign. So for the first example, one might write this as y equals x cubed. This is an explicitly defined function because it's y equals, and on the other side we only have x. And so when we take the derivative with respect to x of a function like this, because the variable down here in the dx matches the variable that we're taking the derivative with respect to, we do what we've been doing. We just say, okay, the derivative of x cubed using the power rule is 3x squared. In the next example, we might define this by saying y equals y cubed. So we've got y's on both sides of the equation. And when we look at the variable down here in our notation, d dx, it does not match the variable that's in the actual function or in the expression, as it would be here. So what we do is we take the derivative as we normally would, but we actually apply the chain rule. So I'm going to go ahead and I'm going to do this as if it was a chain rule problem and say outer, derivative of the outer, inner, derivative of the inner. If we're taking a derivative with respect to x, we know to do chain rule because what's inside the function is something other than just x. In fact, it's completely different from x. So the outer is going to be something cubed. The inner is going to be y. And the derivative of the outer is 3 something squared. And the derivative of the y is going to introduce some notation because when we took the derivative of something like the first example, y equals x cubed, we might write something like y prime equals 3x squared. But another way of writing y prime that we've emphasized in the last couple of sections is we could also write dy dx. So the derivative of y is 1, because that would be the derivative of the variable, dy dx, because it's the derivative of a y. And if we put that all together, then we're going to say 3 parentheses squared. In the parentheses, we put our inner, which is y, and then our derivative of the inner, dy dx. Now that's quite a bit of work for such a tiny, tiny expression. And so what we tend to remember instead, and what mathematicians do instead when doing implicit differentiation, is instead they just say, if I take the derivative of a y, write dy dx next to it. So we're doing the chain rule every single time. We're just not expressing it as outer, derivative of the outer, inner, derivative of the inner. So if I do the next example, we're taking the derivative with respect to x. So our independent variable is x, but we've got an x and a y in our expression. So when we take the derivative of the x cubed, we're just going to take that as normal, 3x squared. We could, if we wanted to, write dx dx, but dx over dx is just 1. It's something over itself, so we don't write it. And then we're going to take the derivative of y cubed, which is going to be 3y squared. So take the derivative using power rule as we normally would for a variable, and then just put a dy dx after it. Okay. So that's taking derivatives with expressions using the notation dy dx. And so usually we just say dy dx, but what this really means is the derivative of y with respect to x. So it's saying x is the independent variable, y is the dependent variable. And so you have to write that notation when you take the derivative of a y and your derivative is with respect to x. So let's try some examples. So the next example says find dy dx. So because I just have 3 separate terms and then an equals 5 on the other side, I'm just going to go right down the line and take the derivative of each of the terms the way we've normally done it, and just keep an eye out for when I take the derivative of a y. So the derivative of 1 is 0. The derivative of minus x is minus 1. The derivative of y squared is going to be 2y, but it was a y, so we put dy dx. And then on the other side of the equal sign, the derivative of 5, well, 5 is a constant, and so the derivative of a constant is 0. Now the instructions say find dy dx, which is another way of saying we need dy dx equals, or get dy dx by itself. So I'm going to take what we have now, negative 1 plus 2y dy dx equals 0. And I'm just going to algebraically isolate the dy dx. So I'm going to add 1 to get 2y dy dx equals 1. And then the 2y is multiplying, so I'm going to divide it. So divide by 2y and get dy dx equals 1 over 2y. Okay, dy dx is isolated, and so we've solved the problem. Let's try the next example. This is actually a circle. X squared plus y squared equals 25 is a circle with radius 5. The instructions say find dy dx, so we're going to take the derivative. The derivative of x squared is 2x, and since it's a derivative with respect to x, I don't have to write any special notation. And then I'm going to say plus 2y, and because that is a derivative of a y, and we're taking the derivative with respect to x, I'm going to put dy dx. And then the derivative of 25 is 0. So then we're going to isolate the dy dx because that's what the instructions say. So we'll subtract 2x and get 2y dy dx equal to negative 2x. We'll divide by 2y and get dy dx equal to negative 2x over 2y, which is fine to leave as an answer, but it also simplifies because the 2's will cancel. So it simplifies into negative x over y. For the next 2 examples, we're going to add a layer. We're still finding the derivative of y with respect to x, but notice we have a term in here where x and y are multiplied together. And so in the past, when we've had 2 variables multiplied together, we've done the product rule. When we did it before, the 2 variables multiplied together were both x's, but the product rule still applies even if it's x times y. So when we start this problem, we're going to go ahead and say the derivative of 4x cubed, so that's going to be 12x squared plus, And then we're going to go ahead and do a box for power or for product rule. So x and y. The derivative of x is 1. The derivative of y is 1, but also remember we have to write dy dx. So I'm not going to bother writing the 1 because it's just going to go away anyway. We'll write the dy dx. So then we get 1 times y, which is y, plus x dy dx. And then on the other side of the equal sign, we have a constant, and the derivative of that constant is 0. And then the instructions say find dy dx. So we're going to get the dy dx by itself. We're going to go ahead and subtract 12x squared and subtract the y. So minus 12x squared and minus y. So that's going to give us x dy dx equals negative 12x squared minus y. And then we'll divide by x. So dy dx is now by itself, and it's equal to negative 12x squared minus y divided by x. In the next example, we have something very similar happen. We have this term that has an x and a y multiplied together. It's an x squared and a y multiplied together, but we have two variables multiplied together. Notice I also highlighted the negative 3. There are a couple of different ways that you can look at a problem like this and how to deal with the product rule. What I would recommend is keeping the negative 3 with the x squared. Okay, it doesn't apply to both the x squared and the y, but let it apply to the x squared. So the derivative of 2 is 0. So I'll start that down there. Then we're going to do the box for our product rule. So negative 3x squared times y. The derivative of negative 3x squared is negative 6x. The derivative of y, just like before, is dy dx. So we start with negative 6x. We're going to say negative 6xy plus, and then it's a negative in front of our 3x squared. So I'm just going to make this minus 3x squared dy dx. And then on the other side, the 10, that derivative is going to be 0. So we've got negative 6xy minus 3x squared dy dx equals 0. And we're going to isolate the dy dx because that's what the instructions say. So we're going to do plus 6xy to both sides. And that's going to give us negative 3x squared dy dx equal to 6xy. And then we're going to divide by negative 3x squared on both sides. And that gives us dy dx equals 6xy over negative 3x squared, which is a perfectly fine way to leave our answer, but it does simplify. 6 over negative 3 gives us negative 2. In the bottom, we're going to have an x because x over x squared leaves us with an x in the bottom, and then we're going to have a y in the top. For the next example, we've got one more example with a product rule. Whoops, sorry about that. So let's go ahead and set this up. So we're going to start off with the derivative of 2y to the 5th. So using power rule, that's going to be 10 y to the fourth. It also was a derivative of a y, so we have to remember dy dx. Then we've got our term with a product rule. So we'll set up our box. So we'll have x and y to the fourth. Derivative of x is 1. Derivative of y to the fourth is 4y cubed dy dx. So we'll say 1 times y to the fourth, so plus y to the fourth. And then plus, and then usually what we do is we put the number first. So this is going to end up being 4xy cubed dy dx. And then that's going to equal 0 because the derivative of 6 is 0. So now in this example, if we're trying to isolate dy dx, we run into a little bit of a snag because we have two terms that have dy dx. So let's take those two terms and let's write them together. So 10y to the fourth dy dx, and then plus 4xy cubed dy dx. And I'm going to move that y to the fourth to the other side by subtracting. So subtract y to the fourth. So now since both of those terms have a dy dx in them, I can factor that out. So I can say dy dx times 10y to the fourth plus 4xy cubed equal to negative y to the fourth. And then I can divide by everything that's in the parentheses. So I can make this dy dx equals, and then I'm going to divide by 10y to the fourth plus 4xy cubed with the negative y to the fourth in the top. And I just wrote it that way because the bottom is longer than the top. So I was trying to space it out. If I wanted to, I could simplify this because the denominator, let me write this in red so that it looks different, has y's in it. It has 3 y's in it. It also is, both numbers are divisible by 2. So I could factor out 2y to the third and get 5y plus 2x. And then the y to the third that's now in the bottom can cancel with 3 of the y's in the top. So I can cancel and make this, so I can cancel 3 of them out and just leave me with 1. So cleaning this up, I end up with negative y in the top. In the bottom, I have the 2 that I factored out. And then I also have 5y plus 2x. And again, not necessary to factor it out that much, but sometimes if you're doing things like solving after you're done with this, it could be helpful. So those were a few examples that had product rule in them. Let's look at an example that has chain rule in it. So for this next one, I know that it's chain rule because inside the parentheses, I have more than just a plain old x. I have x plus y. So I'm going to say outer, derivative of the outer, inner, derivative of the inner. The outer is going to be parentheses to the 7th, which means derivative of the outer is 7 parentheses to the 6th. The inner is x plus y. And when I take that derivative, the derivative of x is 1. The derivative of y is also 1, but it's 1 dy dx. And when I put this together, I say derivative of the outer, just like we've always done. So 7 parentheses to the 6th. The inner is x plus y. And then the derivative of the inner, I'm going to make sure to put in parentheses because it has two terms. So 1 dy dx, 1 plus dy dx rather. And then on the other side, the derivative of 6 is 0. So now I need to go ahead and isolate the dy dx. So I'm going to start by dividing the 7 times x plus y to the 6th on both sides. And that's going to give me 1 plus dy dx. And I've got 0 divided by all of that stuff. So as long as x plus y isn't 0, then I can go ahead and do 0 divided by whatever that is and get 0. And then I'm going to subtract 1. And that's going to leave me with dy dx equals -1. So next we're going to add another layer. We've been doing our derivatives. We added some derivative rules in there. Now let's talk about horizontal and vertical tangent lines. So a horizontal line, remember, is the line that goes east and west. It goes side to side. So a horizontal line, it's important to remember, has a lot of run when we talk about rise over run, but 0 rise. So when we're talking about a horizontal tangent line, what we're saying here is that the change in y over the change in x, and that's what this notation also means because derivative is slope. So the slope equals 0. And our answer should look like a horizontal line. So it should be y equals something, whatever that may be, because horizontal lines, since they go side to side, have the format y equals a constant. So knowing both of these, and knowing that we need a dy dx in all of this, let's take the derivative of this equation that we have here. So the derivative of 9x squared is going to be 18x. The derivative of 4y squared is going to be 8y dy dx. And that's going to equal the derivative of 36, which is 0. So then I know that dy dx has to be 0, so I'm going to say 18x plus 8y times 0 equals 0, which means 18x equals 0. And if I divide by 18, x equals 0. But for a horizontal tangent line, our answer needs to be y equals. So we have x equals right now. So in order to get a y value, when I have an x value, I need a relation between x and y. Well, the relationship between x and y is right here at the very beginning. It's what we were given. So I'm going to be able to take my x equals 0 and substitute it into the original equation. So I'm going to substitute 0 for x, and everything else stays the same. The first term goes away, so 4y squared equals 36. And I'm just doing algebra, so I'm going to go ahead and divide by 4 and say y squared equals 9, which means that y equals plus or minus 3. And don't forget that plus or minus, because what we're doing is we're taking the square root of both sides of that equation. And when you take the square root as you're solving, you have to put plus or minus in front of your answer. For the next example, we've got a little mix of product rule, because I see x times y, and finding the horizontal tangent lines. So let's go ahead and find those. So horizontal tangent line, again, dy dx is equal to 0, and our answer has to be y equals something. So I'm going to take the derivative. So we'll say 2x, x times y. I'm going to do a little box here. So x and y, we've got 1 and dy dx. So our derivative is going to be 1 times y, which is y, plus x dy dx. And then we've got another term, y squared. So we've got 2y dy dx again, because it was the derivative of a y. And then the derivative of 4 is 0. Since we know dy dx has to be 0, we're going to plug that in. So we're going to say 2x plus y plus x times 0 plus 2y times 0 equals 0. So that leaves us with 2x plus y equals 0. And so now we've got an x and a y that's equal to 0. So instead of just having x equals 0, we have both variables in there. So another way of looking at this is that y equals negative 2x. Well, if y equals negative 2x, then I can go ahead back to my equation and I can either say the horizontal, and this is not a horizontal tangent line because it's got an x, it's a slant line. So I'm still looking for horizontal tangent lines. I can say x squared plus x times y, which is negative 2x, using this equation right here, plus y squared, so negative 2x squared equals 4. So that gives me x squared minus 2x squared plus 4x squared equals 4. And so if I combine my like terms, I've got, let's see, 4 minus 2 is 2, plus 1 is 3. So I've got 3x squared equals 4, which means x squared equals 4 over 3. And x, if I slide up here, is square root plus or minus square root of 4 over 3. But remember, that's not what I want. I want y equals. So I'm going to take my x equals and I'm going to put it back into my equation. And I can do them one at a time, or I can do one of them and kind of infer what happens. And so I'm going to, let's just take one of them. Let's take the positive one. And I'm going to say square root of 4 over 3. And I'm squaring it because the x is squared back in the original equation. Then I'm going to say plus square root of 4 over 3 times y plus y squared equals 4. And to save us a whole lot of stressful algebra, because this algebra is looking pretty stressful, this is something you would plug into Desmos. Instead of plugging in y, you would plug in x to try and solve this. So let's hop over there real quick. And we're going to say 4/3. Let me go back. Plus square root of 4/3. I'm going to put the y in front here. And then we're going to say plus y squared equals 4. And sure enough, it gives us 2 lovely decimals that count as our answer. Okay. Now we can do the same thing with the negative. The 4/3 isn't going to change because we squared the square root of 4/3. So if I put a negative square root of 4/3 into that negative square root of 4/3 squared, it's going to be the same. The only thing that's going to change is it's going to change this middle term. So I'm going to go back here and I'm going to make this middle term negative. And that gives me 2 more answers. So now if I put both of them in there so that we can compare numbers, let me put the plus sign back in. If you look, I've got 1.155 down here on the red guy. I've got the negative of that. So this is plus or minus 1.155. And then the outer ones are plus or minus 2.309. All right, so let's try one more. We won't do another one because it's quite that complicated, because I won't give that to you, but I wanted you to see what it looked like. Let's do a vertical tangent line. So for vertical tangent lines, they go up and down, north and south. So with vertical tangent lines, they're all rise. There's no run going on. So what that means is that dx dy is equal to 0. And our answer should be x equals something. Okay? So to find dx dy, what that just means is we're going to do the reverse of what we've been doing with this implicit differentiation. In implicit differentiation, we've been writing dy dx every time we take the derivative of a y. To find dx dy, I take the derivative, and every time I see an x, I write dx dy. So what that means is for the first term, 8x squared becomes 16x, and because it's an x, I say derivative of x with respect to y. And then for y's, the derivative of y squared is going to be 2y. And under this notation, it would be dy dy, which means I don't need to write it because it's just equal to 1. And then the derivative of 64 is 0. So dx dy is equal to 0. So we're going to say 16x times 0 plus 2y equals 0, which means 2y equals 0. So y equals 0. But that's not what we're looking for. Vertical lines are x equals. They go up and down. And so I'm going to go back to my original equation, just like what we did with the example right above this. And I'm going to go ahead and I'm going to put 0 in for y, which means now I have 8x squared equals 64. Divide by 8, and I get x squared equals 8, which gives me x equals plus or minus square root of 8. And if I wanted to simplify this, square root of 8 actually simplifies into 2 square root of 2. But again, you don't have to. All right, quick check. And that's the last one that we're going to do. To find the vertical tangent lines, this equation in this last right-hand box is the same as the one that we did before, so the derivative is the same, except you're going to take that y equals negative 2x and solve it for x instead of y. But again, that was just to kind of stretch our brains a little bit, so that won't be on the notes check.